Okay, I will speak about Grundy domination and four other and some other related invariants. So I will start with, I will just change it here. So I will start with, of course, definitions and examples, and then I will present some general bounds and some relations between these invariants. Then some results about the Grundy invariants in regular graphs, complexity results, and at the end I will say a few words about the connection to linear algebra, and if I will have time, I will also present one very easy algebraic proof of some of our results. Okay, I start with dominating set. So a set of vertices is a dominating set if each vertex outside this set has a neighbor in the set. And the cardinality of the smallest dominating set is the domination number of a graph. So I will use this example all over the talk. This graph has a domination number equal to 2. We can see the dominating set. And of course, because there is no universal vertex, this is the smallest possible dominating set. And total dominating set, so a set of vertices is a total dominating set if each vertex of the graph has a neighbor in the set, and the total domination number is, of course, the cardinality of the smallest such set. Okay, and of course this same set as before is also total dominating set because each vertex in the square has also a square neighbor in the square, so it's the set is also total dominating set. Okay, now I will skip to sequences. We say that a sequence of vertices is a close neighborhood sequence if each vertex in the sequence dominates at least something that was not dominated by the previous vertices of the sequence. So when I put a new vertex, this vertex must dominate something new, something that was not yet dominated. And the maximum length of a close neighborhood sequence is called the Grundy domination number of a graph. And of course, if I take this longest possible sequence, close neighborhood sequence, and if I take the corresponding set, then this set is, of course, dominating set. Thus, Grundy domination number is an upper bound for the domination number. Okay, here is one example, again, the same graph. What do I do? I can first put A in the sequence, and of course, A will dominate A and B. Now I can put B in the sequence, and B will dominate C. Now I can put F in the sequence, and F will dominate itself. And now I can put D in the sequence, and D will dominate, of course, D and E. So I found a close neighborhood sequence of length 4, which means that Grundy domination number is at least 4. And we could also easily find out that there is no longer sequence, so Grundy domination number of this graph is 4. I will use also the word, the term footprinter. So again, if I have a sequence of vertices, V1 up to Vk, then we say that vertex Vi footprint the vertices that are dominated by Vi, but were not dominated by previous vertices of the sequence. So if I return back here, I can say that this last vertex D that was added to the sequence footprints D and E, because other vertices were already, so C was already dominated before. Okay, now in 2016, then Brescher, Henning, and Roll presented the total version of this invariant. So for this version, we need open neighborhood sequences. So again, a sequence of vertices is an open neighborhood sequence. If each vertex of the sequence totally dominate at least one vertex that was not totally dominated by previous vertices of the sequence. And again, so for this definition, we don't need graphs without isolated vertices, because if we have isolated vertices, then they are just, they cannot be included in the sequence. Okay, but if I have a graph without isolated vertices, then of course, if I take this longest possible open neighborhood sequence, then the corresponding set is of course total dominating set. So we can see that Grundy total domination number, which is the cardinality of the longest open neighborhood sequence, is an upper bound for the total domination number. So again, the same example. Now A will totally dominate just B. So I put first A in the sequence, and A will totally dominate B. Now I put F in the sequence, so the second vertex in the open neighborhood sequence is F, and F will totally dominate just C. Now I can put D in the sequence, which will totally dominate just E. And now I can continue by putting E in the sequence, and E will totally dominate D. Now I can, of course, put C in the sequence, so C will, of course, totally dominate F. And finally, I can put B in the sequence because B will totally dominate A. So what we find out is that Grundy total domination number of this graph equals 6. Okay? Then a bit later, two more invariants were Grundy invariants were introduced. Okay, I will not go in details in the motivation here. I will say a few words at the end of my talk. So if we check this definition here, so this is somehow very similar to the closed and open neighborhood sequences, just we somehow combined open neighborhoods and closed neighborhoods. And also here, where we just switch. So what happened? Okay, we didn't just check what happened if we switch this, if we take this combination of open and closed neighborhoods, but what we found out is that Grundy domination number is closely related to zero forcing number. So, and then we found out that if we change a definition of closed neighborhood sequence a bit, so that we take this definition, then we get exactly the dual of zero forcing number of a graph. And that was the main reason to consider this kind of sets. So a sequence of vertices is a Z-sequence if each vertex of the sequence totally dominates at least something that was not dominated by previous vertices of the sequence. So the difference between this sequence and closed neighborhood sequence is that if I put the vertex in the sequence that will footprint itself, then it is necessary that this vertex also footprints something else. So if vertex dominates itself, then it must dominate also something else. Okay, that's the difference. And of course, Z-Grundy domination number is then the length of the maximum. So is the maximum length of such sequences. And then finally, if we can also consider L sequence, which is the sequence of distinct vertices with the property that each vertex of the sequence dominates at least something that was not totally dominated by the previous vertices of the sequence. So, okay, and this L, and then L Grundy domination number is the cardinality of the longest such sequence. So this L sequence is really special. Other three are kind of similar with some similar properties, but this one is really different. The first thing is that we need in the definition distinct here. Because otherwise, of course, we could always create infinite sequence of the same vertices. So we can take one vertex and then repeat this vertex all the time, and we would get infinite sequence. So that's why we have in the definition here distinct. And another thing is in other Grundy invariants, when vertex is dominated, so somehow this vertex cannot be footprinted again. So each vertex can be footprinted just once. But here in L sequence, it is different. So first, so if I just check very easy example, I don't know, P3, I can put one vertex in the sequence, say that this is the first vertex in the sequence, and this vertex by definition footprint V1 and its neighbor. But now when I put the second vertex in the sequence, say that this is this vertex V2, then by this definition, because what is already dominated is just somehow that are just open neighborhoods, then this vertex V2 will again footprint V1. So this one is somehow special because vertices can be footprinted twice. And the vertices that are footprinted twice are just the vertices that footprints the vertices that footprint itself. So if vertex footprints itself, then this vertex will be footprinted again. So somehow this one is special. Okay, so here is the same example for Z sequence. So this Z sequence is quite similar than a close neighborhood sequence. I can first put A in the sequence and then I put B in the sequence. But now what it happens is that I'm not allowed to put F in the sequence, because if I put F in the sequence, F will dominate just itself. And this is forbidden in the Z sequence. So I'm not allowed to put F in the sequence as in the close neighborhood sequence, but what can I do? I can continue by putting D in the sequence. And now finally I can put C in the sequence because C will dominate F. Okay, somehow Z Grundy domination number is again 4, but the close neighborhood sequence described earlier is not Z sequence. But if we check this Z sequence is A, B, D, and C. This Z sequence is also close neighborhood sequence. So somehow already from definitions, we can find out this relation because any Z sequence, what does Z sequence say? We put in the sequence a vertex if this vertex will dominate something different from itself. But this is also fine for the close neighborhood sequence. So any Z sequence is also close neighborhood sequence. And thus Z Grundy domination number is at most Grundy domination number. Okay, so what we have here are some trivial upper bounds for these Grundy invariants. Maybe I comment this Grundy total domination number is bounded with the upper bound is order minus minimum degree plus 1. And what's the reason for that is that when I put first vertex in the sequence, of course, this first vertex will totally dominate at least its neighbors. So this first vertex will dominate at least minimum degree vertices. But what we know is that each vertex must footprint something new, so must totally dominate something new. So what is remains here is order minus minimum degree plus 1 vertices that can still be totally dominated because this first vertex is not totally dominated again. So that's the reason for this bound. Okay, we put first vertex and then what it remains is order minus minimum degree vertices, which can still be totally dominated. Okay. This bound for Grundy domination number is similar, but for L-Grundy domination number, the argument is much more difficult because we know that vertices can be footprinted twice. So this argument that was described here for Grundy total domination number is not fine for the L-Grundy domination number. But anyway, the same bound is also true, and this was proved recently by Herman and Smith. Then we have some other nice bounds for Grundy invariants related to some other well-known graph parameters. So the Edge-Klikauer number, I just selected few such, and those that I selected, I will somehow present again at the end of the talk with some algebraic proof of these results. So the Edge-Klikauer number of a graph is the minimum size of a set of clicks that cover all the edges of G. And so if we have a graph without isolated vertices, then Grundy domination number is bounded above by the Edge-Klikauer number, and the bound is also sharp. So, for example, in complete graphs, of course, Grundy domination number is 1, and Edge-Klikauer number is also 1. And the bound is also tight, for example, in caterpillars. Then we have a similar, then we can relate Grundy total domination number with vertex cover number. So vertex cover number is the minimum cardinality of the set of vertices with the property that each edge of a graph has at least one end vertex in this set. Okay, and then in 2018, Brescher, Kos, Nazini, and Torres proved that Grundy total domination number is bounded above by the 2 times vertex cover. And they proved also that the bound is sharp. So, for example, it's achieved in trees. Okay, and also for Z-Grundy domination number, there is upper bound with another well-known graph invariant, which is path cover number. So path cover number is the smallest number of vertex disjoint paths that cover all vertices of a graph. And Z-Grundy domination number is bounded above by the order minus path cover number. And again, the bound is sharp, so the bound is achieved in trees. So this was proved in terms of zero forcing number. So what is written here is just a direct translation from the result proved for zero forcing number to the Z-Grundy domination number, because as I mentioned earlier, these zero forcing and Z-Grundy domination numbers are somehow dual. Okay, so we have this bound. And of course, also there is a relation between these Grundy invariants. So I already mentioned that Z-Grundy domination number is a lower bound for the Grundy domination number. And of course, directly from the definition, it follows that Z sequence is always also open neighborhood sequence. And thus, we know that Z-Grundy domination number is also bounded above by the Grundy total domination number. Okay, maybe I will just go to the next page. So here is a somehow graphic presentation of the relations between these invariants. So we know that domination number is the smallest among all these invariants. And we know that domination number is, of course, bounded above by the total domination number. Just recently, we proved that if G is a graph with no click component, then Z Grundy domination number is an upper bound for the total domination number. So if we consider connected graphs, then there are just complete graphs are the only exception, where of course total domination number is larger than Z Grundy domination number, because Z Grundy domination number is 1. Okay, but if we have a connected graph different from a complete graph, then Z Grundy domination number is at least as large as total domination number. Okay, we already know that Z Grundy domination number is at most is bounded above with the Grundy total domination number and Grundy domination number. And there is no relation between Grundy and Grundy total domination number. So it's not like in standard domination. So before we had one example where Grundy domination number was 4 and the Grundy total domination number was 6. Okay, so there is an example where Grundy total domination number was more than Grundy domination number, but we can also easily find examples where Grundy domination number is larger. So for example, if I take a star with, I don't know, many leaves, then of course Grundy total domination number in the star is 2. Okay, I can start with the leaf. But now what happens? I totally dominate this vertex, the central vertex. So for open neighborhood sequence, I'm not allowed to put other leaves in the sequence. So the only thing that I can do is I can put the central vertex in the sequence. So Grundy total domination number of the star is 2. But for close neighborhood sequence, I can put all the leaves in the sequence in any order and get close neighborhood sequence of cardinality if I have a star K1n of cardinality n. Okay, so in the stars, the Grundy domination number can be, if star is large enough, then the difference is also large between Grundy total and Grundy domination number. And then I have this L Grundy domination number, which is the largest one, and that's why the notation is L. So L Grundy domination number is an upper bound for Grundy total and Grundy domination number. And moreover, it can be easily deduced that the difference between Grundy domination number and L Grundy domination number is at least 1. Okay, so it must be strictly, so L Grundy domination number is always strictly larger than Grundy domination number. And this can be easily seen because if I take a close neighborhood sequence, for example, let x1, x2 up to xk be the largest close neighborhood sequence. So this means that Grundy domination number of G is k. Okay, then I can easily create a L sequence of cardinality k plus 1. So because this xk was in the sequence, so by the definition, this means that this vertex footprinted something. So this means that there is a vertex, there is a neighbor of xk, or not neighbor, maybe this u can be equal to xk. So this u is from the close neighborhood of xk. So there exists such vertex u, which was not dominated by the previous vertices of the sequence. So u is the vertex that is footprinted by xk. Okay, so xk dominates u, but u was not dominated earlier. But now, what can I do? I can create a sequence up to xk minus 1. This is the same as before. But now I can put u in the sequence. But now what happens? U dominated itself, footprinted itself, which means by the definition that it can be footprinted again. So I can put one more vertex, say u prime, and u prime is an arbitrary neighbor of u. And then this is a legal L sequence of cardinality, at least of cardinality k plus 1. And this means that L Grundy domination number is at least one more than Grundy domination number. Okay. Then K-uniform dominating sequence graphs were considered. So I will say that a graph is K-uniform graph if all maximal close neighborhood sequences are of the same length. This means that a graph is K-uniform graph if domination number equals Grundy domination number. And for example, of course, K-uniform graphs are contained in well-dominated graphs. Okay, so because if we check this dominating chain that was already considered today, if we check this dominating sequence chain, then Grundy domination is the largest in this chain, is the largest number. Okay. So, and then in the seminal paper about Grundy domination number, so these K-uniform graphs were somehow characterized for K equals 1, 2, and 3. So for 1 and 2, we had examples of connected such graphs, but for K equals 3, we proved that there are no connected K-uniform graphs. And just recently, I saw array characterized K-uniform graphs for any K at least 3. So she proved that for any K at least 3, there is no connected K-uniform dominating sequence graph. Okay. And then total K-uniform graphs were also considered. These are graphs with all maximal open neighborhood sequences having the same length. So this means that Grundy total domination number equals total domination number. And if we say K total K uniform, then we mean that these two values are both equal to K. Okay, so maybe first I can explain that we can consider just graphs without false twins. So two vertices are false twins if they have the same open neighborhoods. Because if I have a graph which is total K-uniform, then I can put as many false twins as I want, and I will not change total domination number, and I will not change Grundy total domination number. So the new graph will again be total K-uniform. So first, in the seminal paper about Grundy total domination number, total two uniform graphs were characterized as complete multipartite graphs. And then Brescher, Kos, Mazzini, and Torres proved that there are no graphs with Grundy total domination number equal to 3. And of course, this implies that there are no total 3 uniform graphs. And then this problem was studied in two more papers. First, for example, it was proved that there does not exist a total K-uniform graph where K is odd positive integer. So somehow we know that this such graph does not exist for K equal 3. This was known earlier, but now Bahadir, Gezipek, and Dojgan proved that there does not exist total K uniform graphs for any odd positive integer K. And this was proved in a very nice way. So what they prove is this lemma, which says that if we have a total K uniform graph with no isolated vertices for K at least 3, and of course, we know that K must be more than 3 because for 3 we know that such graph does not exist. Then if I delete the close neighborhood of two vertices which are adjacent, so I delete from G the close neighborhood of U and the close neighborhood of V, which is adjacent to U, then what I get is a new graph which is total K minus 2 uniform and has no isolated vertices. So if we would have a total K uniform graph for some large odd K, then of course we could use this operation many times, and finally we would get a graph which is total 3 uniform, and we know that such graph does not exist. Okay, so what we did, we studied total 4 uniform graphs in false twin-free bipartite graphs. We characterize such graphs, and somehow we believe that there are no other total 4 uniform graphs, so that all total 4 uniform graphs must be bipartite. But then again, by Bahadir, Gizebek, and Doshgan proved that this is not the case, so that the line graph of K6 is total 4 uniform. And of course, this graph is not bipartite. So this means that there exists also non-bipartite total 4 uniform graphs. But they also prove that there is no connected chordal total K uniform graphs, total K uniform graph. Moreover, from this result, that the line graph of K6 is total 4 uniform graph, we can create another total K uniform graphs. So what they proved is that if G is connected, non-bipartite, and total K uniform graph, then the direct product of G with K2 is again a connected and total 2K uniform graph. So what we get is that because we have the line graph of K6, which is total K uniform, total 4 uniform, by this result, we also get existence of total 8 uniform graph. Okay, so we also have some total K uniform graphs for K more than at least 8, for K at least 8. What they also proved is that if G is total K uniform graph, false twin-free, total K uniform graph, then this graph must be regular. So if we want to find all total K uniform graphs, we can consider just regular graphs, because we know that outside regular graphs, there are no total K uniform false twin-free graphs. So my first problem here is, can you find a characterization of all connected total K uniform graphs? Of course, you can consider just regular graphs. Or even it would be already interesting to get characterization of all total 4 uniform, total 4 uniform graphs. So such characterization is known, of course, for bipartite graphs. So what it remains is to somehow consider non-bipartite cases. Okay, then now I will say a few words about Grundy domination number of regular graphs. So Grundy domination number and Z-Grundy domination number were studied in K-regular graphs by Brescher and Brezonik. So they proved a lower bound for Grundy domination number in connected K-regular graphs. Maybe I just explained that this bound is half of the order for the cubic graphs. So they proved that for cubic graphs, Grundy domination number is at least 1/2 of the order. And they also proved that the bound is sharp, and they characterized extremal graphs for this bound. My next problem is, can you find the characterization of all K regular graphs that achieve this bound presented in this theorem here? Okay, so for K equals 3, this characterization is known. So my question is there, can you find a characterization for K at least 4? Okay, then Z-Grundy domination number was also studied in K regular graphs. So Brescher and Brezoning proved that if G is not complete graph on k plus 1 vertices, then Z Grundy domination number is at least n minus 1 over k minus 1 if G has a triangle, and n minus 2 over k minus 1 if G is triangle free. So, but this bound for triangular 3 graphs consists with more general bound that was proof in terms of zero forcing number. Because Amos, Caro, Davila, and Pepper somehow proved that in arbitrary graph, Z Grundy domination number is at least n in arbitrary triangle free graph. Z Grundy domination number is at least n minus 2 over delta minus 1. Of course, for regular graphs, in regular graphs, we replace, we change delta with k, and we get this bound here. Of course, this bound proved by Amos, Caro, Davila, and Pepper was done for a zero forcing number, but translated to the language of Z Grundy domination number, we get this bound. So, and moreover, in 2016, also extremal graphs for this bound were presented. So there are just somehow 3 graphs that achieves this bound. So what Brescher and Brezonik did was improve this bound for the case when G has a triangle. And moreover, they improved this bound for cubic graphs. So they proved that if G is a cubic graph different from K4 and K33, then Z Grundy domination number is at least 1/2 of the order, and the bound is sharp, and they also characterized extremal graphs for this bound. So this is somehow improved. So this n-half bound is better than the bound described in the previous slide. Also in regular graphs, Grundy total domination number was studied. So in the seminal paper it was proved that if G is k-regular graph, then Grundy total domination number is at least n over k. And the bound is sharp, just the bound is attained just in a complete bipartite graph k, k, k. And then this bound, this nice trivial bound was somehow improved. And Brescher, Henning, and Roll somehow presented 2 bounds, one for bipartite and one for non-bipartite graphs. And if we somehow, and this bound here somehow implies a little bit nicer bound, which is n over k minus 1. So somehow it is known that if G is different from complete bipartite graph KKK, then Grundy total domination number is at least n over k minus 1. And what is also known that there is exactly 1 cubic graph, that there are exactly 2 cubic graphs that attain this bound, and exactly 1 4-regular graph that attain this bound. But for k at least 5, it is also known that this bound is that there is a strict inequality. So my next question is, if we remove these 3 graphs and complete bipartite graph KKK, can you improve this bound? Because we know that this bound is sharp just for 4 graphs. For 3, and this complete bipartite graph KKK is special. And my next question is, can we improve the bound that directly follows for L Grundy domination number in cubic graphs? So directly from this inequality and the inequality that Grundy domination number is at least 1/2 of the order, we get that L Grundy domination number is at least 1/2 of the order in cubic graphs. So my question is, can this bound be improved? Okay, now some complexity results. It is known that Grundy domination number problem is NP complete even when restricted to chordal graphs and to bipartite and co-bipartite graphs. And this was just recently proved by Brescher, Pandey, and Sharma. And it is known that Grundy total domination number problem and L-Grundy domination number problem are both NP complete even when restricted to bipartite graphs. And for Z-Grundy domination number, it is known that the problem is NP complete in general graphs. And again, this was proved in terms of zero forcing number. So my next question is, can we say something about the complexity of Z-Grundy domination number problem in bipartite graphs? Because for all other three Grundy invariants, it is known that the problem is NP complete. Okay, then, for example, we can consider trees. So in trees, these problems are much easier. So there exists linear time algorithm for Grundy domination number in a tree, but there is no explicit formula known. For Grundy total domination number, it is known that it is 2 times a vertex cover in the tree. And there is, of course, linear time algorithm that computes this vertex cover and thus Grundy total domination number. And also for the L-Grundy domination number, it is known that L-Grundy domination number of a tree equals the order of the tree. And for the Z-Grundy domination number of a tree, it is known that it is order minus path cover number of a tree. Okay, so somehow these problems are easy in trees. For example, in split graphs, so a graph is a split graph if its vertex can be partitioned into 2 subsets, where one subset is a clique, so it induces a complete graph, and the other is an independent set. Okay, and it is known that Grundy domination number of a split graph can be obtained in polynomial time. Somehow it depends on the independence number, so it is either independence number or independence number plus 1. But for Grundy total domination number and L-Grundy domination number, it is known that this problem is NP complete even in split graphs, and of course, thus also in chordal graphs, because split graphs are a subclass of chordal graphs. So my next question, again, can we say something about the Z-Grundy domination number in the split graphs? So again, this is the only Grundy invariant for which the result in split graphs is not known. Okay, maybe these Grundy invariants were studied also in many other graph classes, so in interval graphs, in co-graphs, in some graphs obtained from some decompositions of P4 tidy graphs, in graph products, Kneser graphs, and many others. Okay, I will not go in details here. So as I promised, I will I will present the relation of Z-Grundy domination number with zero forcing number. So we have a graph and we color the vertices with white and blue. And the color change rule says that if a given blue vertex has exactly one white neighbor, then we will color this white neighbor with blue. Okay? And now, if we have a set of blue vertices B, and all the remaining vertices of a graph are white, and then if by a repeated application of the color change rule, all the vertices of graph eventually turn to blue, then the set B is called a zero forcing set. And the zero forcing number of a graph is the cardinality of the smallest zero forcing set. So this zero forcing number was introduced in 2008 by a large group of people in some workshop. And it is quite very popular topic in last 15 years. So I checked. So this seminal paper has more than 400 citations on Google Scholar, and for example, around 250 citations on MathSciNet. So there are many things known about zero forcing. Okay, and what I will do, I will present this relation to Z-Grundy domination number. So I will return to the same example. So if you remember, we had a Z sequence, which was A, then B, then D, and then C. And why this was a Z sequence? We were able to put A in the sequence because A footprinted A and B, and then B footprinted C, and then D footprinted D and E, and finally C footprinted F. So that's somehow the reason that this is really a Z sequence. But now what I do is I color the remaining vertices of the graph, so the vertices that are not in this sequence, by blue. Okay, and then what happens is that this will be a zero forcing set. And now I just go in the reverse direction. So before, C was in the sequence because of F, because it footprinted F. Now, because F is blue, C will become blue. So if I check now F is blue and C is the only white neighbor of F, so I can color C by blue. Okay, I will do this. I can color now C by blue. And now again, because before D was in the sequence because it footprinted E. Okay, but now because of E, D will return to blue. So D is the only white neighbor of E, so D can be colored blue. And now I can continue. And of course, because of C, B will become blue. And because of B, A will become blue. So what I can see is that, that this set with vertices E and F is a zero forcing set. But this is not just in this case, this always holds. So we prove that the sum of Z-Grundy domination number and zero forcing number equals the order of the graph. Or in other words, if we take somehow the complement of the set that corresponds to the zero forcing set, that corresponds to the Z-Grundy dominating sequence, then what we get is a zero forcing set and vice versa. Okay. So now what we have is somehow this zero forcing number was introduced because it is related to minimum rank of a graph. So what is minimum rank? So minimum rank of a graph is the smallest possible rank over all symmetric real matrices where the ijth entry is non-zero whenever I and j are adjacent, but if they are not adjacent, then it's zero. And we have no restriction in the diagonal entries. And of course, maximum nullity is the biggest possible nullity over all such matrices. And it is known that the sum of maximum nullity and minimum rank is the order. And what was proved in this seminal paper of about zero forcing is that maximum nullity is a lower bound for the zero forcing number. And with our relation, we get that Z-Grundy domination number is a lower bound for the minimum rank of a graph G. Okay, then Lin somehow in 2019 proved that we can change the definition of minimum rank a bit and get other minimum rank parameters that are somehow upper bounds for the other Grundy invariants, not just for the Z-Grundy domination number. So somehow for each Grundy, we have a type of minimum rank such that minimum rank parameter is somehow upper bound for the Grundy, a type of Grundy domination number. So for example, we can define loop minimum rank, which is somehow similar as earlier definition. So the difference is just that we've put some restriction to the diagonal entries. We want that all diagonal elements are non-zero, okay? And then Lin proved that Grundy domination number is a lower bound for such a loop minimum rank. And moreover, he proved that loop minimum rank is bounded above by the Edge-Klikauer number. Okay, and if G is a graph without isolated vertices, and if we combine these two inequalities, we get the bound that we already mentioned, so that Grundy domination number is bounded above by the Edge-Klikauer number. Okay, because I don't have time, I will skip this easy proof, and I will finish with next result, which is a zero minimum rank. So again, the same definition, just the restriction on the diagonal is that the diagonal entries must be zero. Okay, so two vertices, if two vertices are adjacent, then the corresponding ij entry is non-zero, otherwise it's zero, and we have zeros on the diagonal. And this is somehow zero minimum rank, and Lin proved that Grundy total domination number is bounded above by the zero minimum rank. And moreover, he proved that if G is a graph, then zero minimum rank is bounded above by the 2 times vertex cover. And again, if we combine these two inequalities, we get the bound that we already mentioned, that Grundy total domination number is bounded above by the 2 times vertex cover. Okay, and I will just take 1 minute to present this proof that zero minimum rank is bounded above by the 2 times vertex cover. So what do we do? We take a symmetric real matrix A, whose ij entry is non-zero whenever vertices I and j are adjacent in a graph G, and is zero otherwise, and we put on the diagonal zeros. So A is arbitrary such matrix. And that's the reason that we get this inequality. Of course, zero minimum rank is then at most rank of A, because zero minimum rank is the smallest possible rank among all such matrices, but A is just one such matrix, okay? And we get this inequality. And now what do? We have such matrix A, this is my A, and say that X is an independent set. This is X. Okay, what does this mean? This means that if I check the submatrix of A somehow induced by this X, this is a zero matrix, and the rank of this submatrix is zero, of course, because I have just zeros in. But what we know, which is well known, is that the sum of vertex cover and the independence number is the order of the graph. So what it remains here is the vertex cover set. So this set S is a vertex cover. Okay. So and we know that this set S has cardinality, which is vertex cover number of a graph G. But now, how can I build A from this matrix of zero? So if I have this matrix here, how can I get A from this small matrix? I first add beta of G rows, and then I put beta of G columns. And because adding a row or a column can increase rank for at most 1, and of course I added 2 times beta of G rows and columns, I get this inequality here. So rank of A is at most a rank of this small submatrix, zero matrix, which is 0, plus 2 times vertex cover. So I get the bounded zero minimum rank is at most 2 times vertex cover. Okay, so very easy way to prove this bounded Grundy total domination number is bounded by the 2 times vertex cover. Okay, that's all from me. Thanks.
Okay, thank you so much, Tanya, for your nice presentation. Is there any question or remarks?
May I?
Yes.
Yeah.
Yes, yeah.
That's really very nice talk. Thank you very much. I'm wondering, Are there any other relationships with, I mean, connections to linear algebra? So you showed just one of relationships, but maybe there are some others.
Yeah, with Grundy, no. So first, this relation for zero forcing was
Yeah.
done, and because of this relation between zero forcing and Z Grande, we get this relation. But then this nice result of Lin was proved uh, that there exist also other types. So also for the L Grande domination number, you can define the minimum rank that
Right.
present an upper bound, but I don't know for any other relations.
Mm-hmm.
Of course, all these then relations between these minimum rank parameters would then also create, with some other invariants, would then also create a relation to zero forcing numbers. But I don't know of any other, just this with vertex cover and edge click cover number.
I see. Yeah, it is really very interesting. Yeah. Full
Yeah.
semantic. Yeah.
And this is really straightforward proof.
Yeah.
So
Right. Yeah.
you don't
Right.
need a
Yeah.
lot of algebra to know to get this. So yeah.
That's right. Yeah. Exactly. Yeah. Okay. Thank you so much.
Okay, thank
Thank
you.
you. Thank you, Elena. Tanya, if I understand correctly, you use the notation L. Why you use notation L and Z? I think Z for zero forcing. Yes.
Yes, because this it was introduced because we found out the relation with zero forcing.
With
Yes, yeah.
okay, and what about L? Because it's the largest, maybe.
Yeah, for L, there is no nice motivation, but if you check these definitions of close and open neighborhood sequences and then of this sequence, so all possibilities of open and close were somehow considered just this last one. Okay, and then
Uh,
we asked, okay, what happened if we change here? And then we
mm,
found out that this one is really the largest. So it's
uh,
usually uh, quite bigger than other ones. And the notation is just because, yeah, of
okay,
that's the
okay,
reason for the notation. Yeah.
okay. Thank you so much. If there is no another question, let's to thanks Tanya again. Thank you so much, Tanya, for your nice presentation.
Okay. Thank you.